All right. So we have a very interesting presentation today now. We have Howard Penrose, call him the MotorDoc. He's the president at MotorDoc LLC, and he's going to be talking to us about an introduction to electrical and current signature analysis for mechanical systems. This is going to be interesting. I'm going to let Howard just get right to it.
Yeah, I have too many slides, and apparently there's so many people watching today that we had a breakdown. So go ahead, go on to the next slide, please. That's just me. I'm sure that they'll make the slides available. Go on to the next one, please. Okay, so basically, what we're looking at is just a quick overview of what electrical signature analysis and current signature analysis are. What's really kind of interesting is people, because they hear the term current and electrical signature analysis, make a really big assumption. And that assumption is that it's meant for looking at just the motor, or it's meant for just looking at the rotor or other electrical components. In reality, when it was developed by Oak Ridge National Labs in the 1980s, it was meant for looking at lubrication and wear issues in bearings and gears in motor operated valves, with an extension of looking at things like belts and other mechanical components in the driven equipment. Now, this was in the 1980s. I believe for those looking, full screen should be that little square box in the presentation. Not sure how else to do it, but in any case, as we look at this, and what we'll present today is on the mechanical systems. So if we go to the next slide, please. The transducer that we're dealing with is the air gap of the machine. This gives us a couple of benefits. One is it allows us to look at the entire system at once versus just a single component, like just a bearing or just one other piece. It also is not load dependent, which is kind of nice because of the way we do it, whether I'm looking at a machine that's 20% loaded or I'm looking at a machine that's 120% loaded, the amplitudes don't change, meaning that I can trend regardless of the load on the machine. Next slide, please. And what we're looking at is a combination of current signature, which will be from the point of test downstream of where we're analyzing, voltage signature analysis, which is upstream. So basically an electric motor would be current signature analysis, and the ultimate high end would be the generator, which is voltage signature analysis. And what we're going to cover a little bit today includes generators. So we're going to look at an elevator application. We're going to look at some wind turbine applications. Next slide, please. The analysis, the best approach is an FFT analysis, which allows us to look at the spectra, just like in vibration. And then we convert that to decibels. There is a linear or demodulated spectra in virtually everybody's technology that you can look at, but it's completely useless for the analysis itself unless you are looking at a constant load across a period of time without any variation. The decibel analysis basically gives you a relative load in relation to your peak voltage or current. So as we go through that, that allows us to become more sensitive, not just to the existing defects, but what is the relationship between all of the different components in the system. So it may be that we have a condition that's driving a problem. In electrical signature analysis, you will see that relationship, versus if I go in and say I take a reading on a bearing and I see that the bearing's going bad, but I have to take a whole lot of other data to figure out exactly why that's occurring. Next slide, please. So let's jump right in and let's think about what's going on out here in the actual driven equipment. So the top one there, that is a gearbox for a wind turbine. I'll show you how that's broken down. That particular machine stood as tall as myself, and I'm just shy of 6 foot. And then the one there on the lower left, that is an elevator motor in Manhattan in an 11-story building. So that's a people mover. Next slide, please. So we'll start with the people mover. So this particular case, what we're looking at is a right angle gearbox motor. So we have a bull gear and we have a worm gear. And what was kind of fun about this, and the reason that picture's on there, is in order to analyze this, we had to count the number of teeth in that picture and count the number of teeth that would be meshing with that from the worm gear. The worm gear is the driven one from the motor, and the bull gear is actually what turns the sheave, which moves the cables, which raise and lower the elevator. As you can see in that top right picture, you see what looks like little bubbles. I know it's a little challenging, but you see what looks like little bubbles there. And what that is actually brass. So as we go through this is wear and tear on there because they had not been changing the lubrication in that gearbox. They ended up doing a lot of wear and tear on the machine in combination. They put the wrong gearbox oil, but in combination with the type of driver they changed from an old DC machine to a decade before they switched to an AC machine, which started wearing away at the brass gears. So next slide, please. When analyzing this, in addition to knowing that ratio, in this case, it's 108 teeth to 2.5 teeth. So I would go 2.5 divided by 108 times the RPM of the motor, and that's the output speed of the gearbox. In addition, I can take a look at as we move forward, I'll be able to take a look at the bearings. Now, one of the challenges with electrical and current signature analysis, I'll use those interchangeably. So we're going to be primarily for this one looking at current. So as you can see on the nameplate, it says bearings 6311 and 6311. Well, they're both turning at the same speed, and I'm seeing both at the same time. So what happens if I see a bearing defect in one of those? Well, I just don't know which one it is. good news is it's a 25 horsepower motor, so chances are if I have a bad bearing, the whole motor's coming off and you're replacing both bearings anyways. But when I get into larger machines, say a wind turbine, where I have a 6330M, 50 odd pound bearing, and access to either side takes a half a day, that becomes more important. So usually what we do is identify one or the other, and then we'll, using vibration or another technology after we've detected a problem, so that we just focus on the one with the problem. In any case, in this case, we know the output speed at peak 60 hertz is 24.4 RPM. However, it's a variable speed application with people on it, so it doesn't immediately go from 0 to 24 RPM. Otherwise, you'd have broken ankles and bonked foreheads. Next slide, please. And then also, as I take a look at it, these are the bearing multipliers. What's really kind of nice for us doing this type of technology is, other than the fact that everything happens in pairs instead of one times, the multipliers are the same. So a bearing defect shows up at the running speed times whatever the multiplier is, and usually can be detected rather early. And so when I show the last presentation, I'll show you how early it can be detected. But in this case, we'll see that there's some specific defects. Next slide, please. So this is how long it takes to go from the first floor to the 11th floor. That's the flat spot in between. The large bulges at either side, that is the machine, that's the elevator basically standing still and then accelerating and then going at a constant speed from the first floor to the 11th floor, and then decelerating and then being held in place before the brake closes. Well, as you can see in the middle slide, which is the conversion of that signature from 0 to acceleration to constant speed to deceleration to 0 again, causes, well, that slope that you see in the middle signature, which is my FFT of the current signature in decibels, and we'll be counting from that top of the line frequency down to whatever the peaks are. But you see that slope. That's because that line frequency has gone from 0, slid all the way up, and then all the way back down again. Well, what can I do about that? So what I'll end up doing is taking a slice out of the signature on top. It'll reduce my resolution a little bit, but I can go all the way down to 10 seconds and still have pretty good data. If I need something greater than that, then there's adjustments you have to make to get better resolution. But if I take that snapshot in between, you'll see what's on the next slide. And that is literally, once I take that one part in the center, now sometimes I have oscillating loads. What ends up happening is it gets filtered. But in this case, when I take that centerpiece, as you can see, the two gold arrows in the middle, those are actually casting voids in the rotor. Do I worry about casting voids? No. In the 1990s, everybody panicked over casting voids and cast aluminum rotors. Well, every cast aluminum rotor has casting voids. It's just that's all that some of the technologies could identify, so they said it's a bad thing. But if the motor's not stalling in a VFD application, it's not vibrating, and you're not seeing bearing failures, then it's something that's easily lived with. It doesn't shorten the life of the machine. It just has to be balanced out. The green ones next to it, those are going to be the cage frequencies related to the bearing. That was what we calculated. And then the next one's out of the worm gear. So now we know that it's not actually the bull gear that's wearing, it's the worm gear. That's the mesh frequency. And then the last one, the red arrows point towards the outer race of the bearing. You'll notice we're not right at 60 hertz, so we have to pay attention to whatever that is. Let's go ahead on to the next slide. So let's take a look at a wind turbine. And one of the nice things about electrical signature analysis and these, towers And people think there's elevators in the towers, and those of us who actually do the work kind of chuckle. And if you've met me, you know I don't like to climb. That's cardio. I'm a power lifter. Anything more than 5 is cardio. So five steps up a ladder, forget it. I'm out of breath. Just kidding. In any case, how can we test these without a climb? A majority of the towers actually have all the controls down tower and lower voltages. And as you can see in that image there, we're actually connected to the control side, which means that we don't even have to shut down the tower, which makes it very nice. So I've been able to, over the last 3 years, test over 4,000 of the 70,000 towers in the United States, so of all types. So we have a definite idea of what's going on with these machines. One of the things happens to be gearbox related issues, and another one happens to be bearing and lubrication issues. One of the nice things is we're seeing everything. So we see this through a generator. We also see the transformer, the coupling, a 3-stage gearbox with a planetary gear set, all the bearings and gears, and the 2 main bearings, which are very large, usually double roller. And the double roller ones, when we see an outer race signature, that generally means they haven't been lubricated properly. That's the number one thing with those that leads to their failure. And one of those failures equates to 800 to 1.2 million US. So it's a significant impact, let alone the months that the tower is out of commission. Let's go on to the next slide, please. And here's what some gearboxes look like. The one on the left would be for a Vestas machine. The ones on the right would be for GEs. And we'll go on to the next one. And in general, this is what they look like. So I have my pinion up at the top. That's going to be my high speed. That's going to be 1,200 or 1,800 RPM. A majority of the towers are 1,200, but there's plenty that are 1,800 RPM. Then there's a central one, and then a what they call the hollow shaft gear. So that's my 3 stages. And then you have planetary. Sometimes they're a dual planetary, but a majority of them are a single planetary gear set. The planetary gear set, which is generally turning 14 to 20 RPM, it sees a lot of the stress. So we usually will see either a planetary gear problem or high-speed gear or bearing problem. Go on to the next slide, please. And this is probably the worst turbine we've seen. It would operate for a whole 2 minutes, which gave us enough time to get data. What you're seeing is voltage and current laying on top of each other. Why? Well, it's a wind turbine. I have to look at voltage and I have to look at current. By definition, this particular design is both a generator and a load. So we're able to pick out by using a high enough resolution, which means we're taking 12,000 samples per second with an FFT block of 65,536 in order to get a resolution down to 0.005 hertz. We need that because, as you can see, all of these peaks in the center around line frequency, those are bearings and gears and other things on the low speed side. And then as we get up in speed, onto the next slide, please. We need that 6 kilohertz. We need that 12 kilohertz in order to get 5,500. The 5,500 hertz is the roll off. So we get out to a 5,500 hertz, technically 6 kilohertz in some applications. So basically 300,000 CPM, which allows us to look at gear mesh issues and multiples of that. Firing frequencies of the drives, which is the circled part on the right, is actually the second harmonic. And then eccentricity related issues, which all drive towards the different problems associated with the machine. In this case, they thought they were tripping because of the generator. It actually turned out to be all of the problems, gear meshing and binding, going on in the gearbox, and they weren't able to run it long enough to analyze it with other technology. And they didn't see the problems with the boroscope. On to the next slide, please. And just another angle. This was a high-speed thrust bearing detection in that same gearbox. It looks like it's buried in there. It is. Some of the peaks can be challenging when you have a disaster like this, but they stand out separately when you know what the data looks like. And the next one, please. And the biggest binding in that, by looking at the actual air gap torque, was the planetary gearbox bearings and the high-speed thrust bearing. On to the next slide. Let's see if we can finish this up. Oh, my video isn't running. Oh, too bad. In any case, just to again put this into perspective, we're talking about a tower that on average starts at, the old GE 1.5 started 80 meters to the center. That's 240 feet. That's a little bit of a climb up a vertical ladder. Sometimes they have climb assist, which means you hook on, it reduces about 35 pounds from your weight. And other times they may have some new types of elevators. But generally, if you're lucky, the climb assist works. So you usually find these guys are in pretty good shape that have to climb with fall protection and everything else. So to try to avoid that and avoid wear and tear on the technicians, plus being able to knock out 40 to 50 towers in a day, the ability to test from down tower becomes very important. The ability to test fast enough so that as we do this next case study, we got lucky. We had a tower where they were able to replace a bearing. Go ahead on to the next one. And right before and after, we were able to take a look. So this is a 1.6, they're actually 1.7 megawatt towers. They are what's called a GESS. So they're 85 meters to the hub, 85 meter diameter blade, and 690 volt output. The bearings are 6330M. We are looking in this one at specifically the gearbox and generator bearings. So on to the next slide, please. In this case, they had just replaced the bearings. Somebody else had just replaced the bearings. The service company went out to take a look. They saw on the bottom, the red arrows, that's voltage signature, identified both a high-speed thrust bearing and the generator bearing. So on to the next slide, please. One of the nice things about taking both voltage and current on the bottom right, what you'll see is in kilowatts, we can actually measure the defect loss, meaning the actual kilowatts lost across a defect. In this case, the total losses between the thrust bearing and the inner, outer, and ball spin for that bearing was about 11 kilowatts in a very lightly loaded machine. So basically, the machine was putting out about 200 kilowatts and losing 11 kilowatts based on the bearing. Next slide, please. And this is what it looked like. So how early can you detect a bearing? Everybody tries to tell me, you can't tell until whenever. Well, you can see there's just a little bit of false Brinelling on the inner and outer race. And then on the right-hand side, you can see where the ball was getting trapped in the cage and dragging a little bit. So this is a very, very early bearing wear. As a matter of fact, the bearing had only been in place for about a month, and then we had the before reading. And after the same day that this was replaced, we actually had the exact same wind conditions. Next slide, please. Meaning that we had a direct comparison. And as you can see on the lower right, you will always have losses. You will always measure kilowatt losses in bearing frequencies. There's always some level. You can tell what kind of lubrication issues you're having by changes in those losses. And as you can see, we dropped it from 11 kilowatts to 2.4 kilowatts by just replacing that. And you can see the thrust bearing is no longer the tallest peak. Next slide, please. And all of those other peaks went away. And amazingly, I got done within 30 minutes. So next slide, please. Which is the opportunity to ask a few questions. And by the way, the picture there, that's a service gentleman testing the same type of tower right at the base. And as again, you can see no exposure to high voltage.
Wow. Now I know a lot more about these things, and I'm going to be very careful. Every time I enter an elevator, I'll be thinking about you, Howard.
Well,
I know
I'll
we
put it
have.
into perspective. The MetLife building in New York City has 69 passenger elevators plus freight elevators. So,
Oh my
people don't think
gosh.
about that. There's quite a bit.
That's quite a lot. We have a question from Stephen though, and it's a bit of a bit long question. What is the calculation for bearing frequencies? Cage, outer race, inner race. Is it similar to how the frequencies are calculated in vibration, or does the software have built-in database with bearing numbers? Very interesting question.
Okay, it is calculated the same way, and I'm going to just do the commercial bit because you did ask the question. In our software, there's
Mhm.
over 65,000 bearings, virtually every manufacturer, including some I've never heard of. And the software uses that data, and everything I just showed you, by the way, was automatically detected by the software and told us what was wrong. We didn't have to go in and do all that analysis. So the analysis, as soon as the data is taken, it pops up and says, you've got this bearing, this problem, this gear, this whatever. And the only thing that we have to do is say, okay, I've got this problem, this problem, this problem. That means this is the issue. This is what's driving it. But yes, it is a built-in database. As a matter of fact, we have people that use the technology plus do vibration, like me, and I'll use the database to get my multipliers.
And we have another interesting question here from Rich, which is asking, is it necessary to force rotation of the blades while evaluating the signature to induce rollover of any defects while monitoring for blade bearing issues?
Good question.
That's a big
Actually,
one.
the generator has to be generating, and by definition, that means that the blades are turning. Um,
Oh,
yeah,
okay.
it doesn't work the other way. We don't forget to turn the fan off. Uh, no, the tower will be running. The question comes in depends on the wind. So if I have 32.2 meters per second, which is where a majority of towers will do what's called cut in, they'll start. Um, I'll detect the problems, but I have to look at all the signatures and I have to look at a bunch of noise because the controls are dumping what's called VAR correction in to correct for power factor and other electrical conditions and to stabilize the grid. It isn't until we get up to about 5 to 8 meters per second that things begin to stabilize, and usually over 10 meters per second wind, so about 20 miles per hour, a little over 20 miles per hour, for us to have full power coming off of a turbine. There's actually a power curve. So, yeah, the towers turn, and you bring up an interesting point. If the blades aren't aligned properly, because they tilt, right? Um, they tilt so that they can catch the wind and vary based upon wind gusts and everything else. I mean, heck, 100 meters out what the wind's going to be. So, anyways, pitch the blades, but and then the yaw which is the changing of the turbine position. But anyways, we will detect when they're not aligned properly. That shows up as what's called a blade pass frequency. And if you don't have the resolution, it mixes right up with what's called a pole pass frequency, which is the indicator for rotor related problems. One of the indicators. There's four
Wow.
indicators we need to detect rotor problems. It's a little more complicated than a motor or a generator. That's one of the
Mhm.
reasons why we're the only technology of this type that's in the wind industry right now.
Oh, yeah. So we are just out of time, Howard. It's always good
I'll
seeing you
take
and
any
talking to
questions
you.
afterwards. People want to
Yes,
reach out to me. I'm always available, and I'll be watching
always.
everything else in the meantime.
All right. Thank you all so much. We'll see you all soon. Bye.
Bye bye. Thank you.